Okay guys, today we're going to be doing mindful percent manipulations. This warm-up, it should say 220% annual rate of growth, right? If they don't specify it's an annual rate of growth, you're going to assume it's an annual rate of growth because that's the standard, right? But today's lesson, mindful percent manipulations, we're going to be converting things like an annual rate of growth to different time spans. So like what's the decade rate of growth or the monthly rate of growth. Alright, so that's today's topic. But before we do that kind of stuff, why don't you guys go ahead and try this warm up. So pause the video and give that a go. Alright, so hopefully you tried them. And this first problem, by the way, a 220% annual rate of growth, that is massive. That is not something we normally see with most things. Like a typical rate of growth for a problem might be like 5% or like 2% or like 3.6% or maybe 25%. All right, but 220%, that's really, really fast. And if you know anything about Bitcoin, that's because that's how fast Bitcoin was growing between those years. So, if Bobby had invested $370, how much would he have 1 year later? So this is exponential growth, and I know that because it's a rate of growth. The value of it was increasing. So a lot of people might think, oh, I can just multiply by 2.2, right? 220% as a decimal is going to be 2.2. Right, so if something's growing by 220%, you might think it makes sense to multiply by 2.2, but we have to be careful, right? This 220%, that is the R value. That's the rate of growth. So that R, that's coming from our formula from Monday. I think I wrote V of t on Monday. I actually don't know why I did that. I think I used V for value. I'm going to change that, I'm sorry, to A for amount. And simply because I use A sub 0 here, so like the initial amount. It doesn't really matter what letter you use, but I'm going to change it to A of t today. So the amount of something after time t is going to equal the initial amount times 1 plus r, if it's rate of growth, 1 minus r, of course, if it's a rate of decay, or something's decreasing, to the t power. So in this instance, after t years, in this case after 1 year, yeah, that's what we're looking for. So we're looking for the amount after 1 year. So A of 1 is going to equal the initial amount invested, which was 370, times 1 plus 2.2 to the first power for 1 year. So we're not multiplying by 2.2, we're actually multiplying by 3.2 here. Right? 2.2 is our rate of growth, but 3.2, that is going to be our growth factor, what we actually multiply by. So after 1 year, he's going to have $370 times 3.2, and that's going to be $1,184. Not a bad investment. All right, so sometimes these percentages are a little confusing for people when they're more than 100%. So let's try to do like another number to see if it makes sense. Let's say instead of a 220% growth rate, it was growing at 100%. Well, if something's growing by 100%, that means it's growing by all of itself, 100% of itself, right? In other words, it's going to be doubling. And in the formula, it would be 370 times 1 plus 1, right? Because a growth rate of 100% means 1. So our growth factor is 2. We're going to multiply by 2 each time when we're growing by 100%. When we're growing by 200%, it doesn't mean we're doubling. It means we're tripling, right? Because then it'll be 1 plus 2. All right, so hopefully you see why when it's a 220% growth rate, we're going to be multiplying by 3.2. We're going to be more than tripling in this instance. All right? Number 2 here, again, this is going to come straight from using this formula. A house purchased 5 years ago for $100,000 was just sold for $135,000. So the amount after 5 years, that was $135,000. That's going to equal the initial amount that it was bought for or sold times 1 plus R. We're looking for the rate of growth here, and after 5 years. So it's just solving this equation. Dividing by 100,000 on both sides, we get 1.35 equals 1 plus R to the 5th. Let's take the 5th root. The 5th root of 1.35 equals 1 plus R. And that's going to be about 1.0618 dot dot dot. That is going to equal 1 plus R. Right? That's going to equal our growth factor. Alright, this is what we're multiplying by each year, our yearly growth factor. So to get the yearly growth rate, which is just R, we're going to subtract 1 on both sides now, and that's 0.0168 to the R. So it's said to round to the nearest 1/10 of a percent. Alright, last year, something that a couple kids did, because I never talked about it, is they rounded this to 0.01, I'm sorry, not 0.01, 0.1, and said that was the yearly growth rate to the nearest 1/10 of a percent. Well, it says nearest 1/10 of a percent. This here is not written as a percentage yet. So this as a percent is 6.18%. Right? So this is the number we want to be rounding. Nearest 1/10 of a percent means this percent value rounded to the nearest 1/10, which of course is 6.2%. Alright, so that is to the nearest 1/10. Don't round this to the nearest 1/10 because that is not written as a percentage yet. And that's really all I wanted to talk about with that one. Alright, so on to our main topic, which is mindful percent manipulations. The country debt of Tanzania is growing by 5.3% every decade. That means every 10 years we have this growth factor. That's our decade, sorry, not a growth factor, growth rate. That's our decade growth rate, which means our decade growth factor is times 1.053, right? And I want to start with this decade growth rate or growth factor and find out what our yearly growth rate and our bi-yearly, so every 2 years, and what is the growth rate for every 20 years? What percent rate is the debt growing at each year, every 2 years, and every 20 years? So drawing a diagram for this first one to find the yearly growth rate, let's say we start with some initial amount. I'll call that A sub 0. And then 10 years later, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to have the debt after 10 years. And to go from our initial debt to the debt after 10 years, well, we're going to use the decade growth rate, which is 5.3%. In other words, we're going to multiply our initial by 1.053. Right, just move that over two places. And this here is our decade growth factor. So to get the yearly growth rate, I need to get the yearly growth factor first. So I know going from there to there again, I'm multiplying by this 1.053. So what do I need to multiply by to go one step or 1/10 of the way there? So you can't just divide this by 10 because it's not linear, right? It's exponential. So again, think about it. I'm multiplying to go from here to there by this number. What would I multiply by each time if I had to take 10 steps? Alright, so the answer is going to be the 10th root of 1.053. Right? I would multiply by this amount. All right. Pause the video and think about it for a second. If you didn't get that, see if that makes sense. Right? Because of course, I'm going from there to there. It takes 10 steps. So if I multiply by that quantity 10 times, I should get 1.053. And of course, if I take the 10th root of 1.053 and I raise it to the 10th power, well, I get the decade growth factor. So that means this value here, the 10th root of 1.053, that is the yearly growth factor. That is what we're going to multiply by each year. So this quantity over here, this is our yearly growth factor. So the way we write a yearly growth factor is 1 plus r, right? If we go back to the warm-up, I'm just going to rewrite our general formula for exponential growth again. Again, remember, 1 plus r, that together is the growth factor. So 1 plus r in this case is the 10th root of 1.053. So to find the yearly growth rate or the percent rate, I take the 10th root of that and subtract 1. And hold on, let's see what we get. The 10th root is approximately 1.005177. Right, 1 plus r is equal to that. So r is about 0.005177. And it says round to the nearest, alright, 10th of a percent. I guess that's fine. Alright, again, we're not rounding this, we're rounding the percentage. So as a percentage, that is about 0.5177%, or about 0.5% if we're rounding. Right, so that is our yearly growth rate. Each year we're growing by 0.5%. Right, and you can see that's clearly not just 5.3 divided by 10, 0.5177, right? And again, that's because it's not linear. This is exponential growth. So you have to do what we just did to get the yearly growth rate. And it is about 1/10, right, of the decade growth rate, but not exactly. Oh yeah, and everyone knows a decade is 10 years, I hope. So, to get the bi-yearly, what percent rate is the debt growing at every 2 years? Well, there's two ways to do this. I can take the yearly growth rate now and square it. Because if I want every 2 years, well, every 2 years, that's going to be over here after 2 years. That would be times this quantity 2 times. So I can take this quantity and square it to get the bi-yearly growth factor. So I can take that also, but really the bi-yearly growth factor is going to equal the yearly growth factor, which is this, right, squared. And if I do that, that is the 10th root of 1.053 squared. Right, I'm using the exact value, which is this, because that's a lot more accurate. If you don't like that, because that is confusing to a lot of people, right, we can take this, the decimal approximation value, and square it. So our yearly growth factor was 1.005177, ... Right, get as many decimals as you can. And so the bi-yearly means that times itself twice. And so 1 plus the bi-yearly growth rate is going to be, let me just type this in real quick, about 1.01038, a lot more decimal places, or 0.01038, and to the nearest tenth, You should all be approximately symbols, by the way. 1.038%, or about 1%. All right, so I used the yearly growth rate here to get the bi-yearly growth rate, but I could have also used the decade growth rate again. It would be exactly the same thing as we did here, except instead of 10 years, or 10 steps, I'm going to do 5 steps. Is that right? 1, 2, 3, 4, 5? Yep. So we would take the fifth root of this amount, and that should, of course, give us the same answer that we just found. So using the decade growth rate or growth factor again, I could also say 1 plus the bi-yearly growth rate is going to equal the fifth root of 1.053. All right, so our bi-yearly growth factor is equal to the fifth root of the decade growth factor, and solving for this again, that's going to be exactly the same. All right, cool. And so every 20 years, that means I can take the decade growth rate, or growth factor, which was 1.053, and I could square it to get the every 20-year growth factor. And solving for r sub 20 here, let's see what that's equal to. That should be about 1.1088, or in other words, about 1 plus r sub 20. So the 20-year growth rate is 0.1088, rounding to the nearest tenth. That's going to be around 10.9%. Right, so again, it's not just this number times 2, right? It's a little bit more than that. Think about how we can find this answer using the yearly growth rate or the bi-yearly growth rate. Well, using the yearly growth rate, it's just going to be our yearly growth factor, right, to the 20th power. 1 plus r sub 20 would also equal 1.005177. Right, you definitely want to use as many decimals as you can. Definitely don't use this rounded value because they're going to be way off. You can also do this to the 20th power and get R20 this way. We could use the bi-yearly growth rate and think about what power we would raise that to. We raise that to the 10th power, right? And again, we want to use as accurate as possible, so something like that to the 10th power would also let us solve for the 20-year growth rate. All right, good. And okay, we'll just leave it at that. So number 4, population of wombats is growing at a constant percent rate. This is a picture of a wombat, by the way, if you don't know what a wombat is. They're actually pretty big. So if the population of wombats starts at 1020, a year later it's 1079, what is its yearly percent growth rate to the nearest 100th of a percent? So going to use the formula again. I think I still have it copied and pasted. Yes, I do. All right, so the amount of wombats I have at the end is 1079. I started with 1027, 1 plus r, and this was after 1 year, so just t is 1. So solving for this, 1079 over 1027 equals 1 plus r. And so, let me type this in my calculator. R is going to be about 0.0506329 ... Change this to a percentage first before doing any rounding. Try to get as many decimals as you can. 5.06329%. And finally, now we are going to round to the nearest hundredth of a percent, 5.06%. Right? And again, some people round this value. Don't do that. Round the percentage. So leave as many decimals as you can along the way. We will assume that the rounded percent found in part A continues for the next decade. So I'm specifying to use the rounded percentage. To find the population in 10 years, what do we need to multiply the original population by? So I'm growing by 5.06% each year, which means I should multiply by 1 plus 0.0506 each year. And that's each year. So in 10 years, I'm going to multiply by that to the 10th power. Right? So this is going to be equal to our, so 1 plus 0.0506, that was our yearly growth factor. Right? This is what we multiply by each time to figure out what we will have after 1 year. So once we do this to the 10th power, well, that's going to be our decade growth factor. Right? We can multiply by this new amount over here to figure out, well, what do I need to multiply by each decade to see what it's to see how much I have afterwards. So this is about round to the nearest 10 thousandths. So hold on. 1.0506 to the 10th power, that's going to be 1 point, that's nearest 10th, 100th, thousandths, 10 thousandths. So 1.6382. Yeah. So what do we have to multiply the original population by to find what it's going to be after 10 years? This is our answer. 1.6382, and what that's called, what we found, is the decade growth factor. It's what we multiply by. So to get the decade percent rate, 1 plus the decade rate, that's equal to 1.6382, which means our decade growth rate is 0.6382. Then tell you to change it to a percentage, so you can just leave it like that. But as a percentage, that is equal to 63.82%. So every decade, they're going to grow by 63, 64-ish%. Right? Each year, they're growing by around 5%, which means in a decade, they grow about 63%. Right? So all the examples we've done so far are examples of exponential growth. This one here is going to be an example of exponential decay. So world oil reserves are depleting by a constant 2% each year. We would like to determine what the percent decline will be over the next 20 years based on this 2% yearly decline. Right? And evaluate an expression for what we can multiply the initial amount of oil by to find the amount in 20 years. So if it's a 2% yearly decline, our yearly growth factor is going to be 1 minus 0.02, or 0.98, right? This here is our yearly growth factor. So we multiply by each year to get what we have left over, right? We have 98% of the previous year if we were losing 2% each year. So in 20 years, we're going to multiply by 0.98 20 times, or to the 20th power. And that's the answer. If you want it as a decimal, this is approximately 0.6676 ... Use your answer to A to determine the percent decline for 20 years. So after 20 years, we're going to have, again, that was equal to 0.00 0.6676. That was our, this here is our, what was it, 20 years? All right, this was our 20-year decay factor. So to find the 20-year decay rate, well, this is going to be 1 minus r, not 1 plus r, because it's a decay in this instance. So negative r is going to be approximately, let's subtract 1 from both sides. That's going to be about negative 0.3324, which means the 20-year rate is about 0.3324, or 20-year rate is about 33.2, did I say what to round to? 33.2%. All right, take a second, see if that makes sense. Again, if you have any questions, please ask me on Classroom. Post a comment on the video. Maybe some other people can answer the questions for you. But yes, this is a pretty tricky topic. A lot of people struggle with this because it's just different, and you have to think about really what's going on. So just going over this problem one more time. We're losing 2% each year, so we're having 98% of the previous year, right? So we can multiply by 0.98 to figure out how much we have after 1 year. So to figure out how much we have after 20 years, we can multiply by 0.98 to the 20th power. So in other words, that's equal to that. That means after 20 years, we have 66.76% of what we had 20 years ago. So to find the percent decline, well, you have to do 1 minus this value, and that's what we get, 0.3324. So there's a 33% decline after 20 years. All right, what would the monthly percent decline be? Well, we know the 20-year decline. We also know each year. So let's start with each year. That's a lot easier to think of. If I want monthly, I will take the 12th root of 2%. Right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here's my starting value, which was, we don't have any starting value here. It doesn't matter what it is. But in a year, each one of these steps represents 1 month. Right? In a year, I multiply by 0.98. Right? That is our 2% yearly decay, which means that is our yearly growth factor, or decay factor, sorry. So we want to find what we're decaying by each year. Instead of multiplying by 0.98, we're going to multiply by 0.98 to the 1/12th power, right? Or the 12th root, because we know we need to multiply by this 12 times, right, to get to 0.98. So 1 minus r monthly is equal to, each month we are multiplying by the 12th root of 0.98. So that is our monthly decay factor. So we solved this to get the monthly decay rate. All right, just like with exponential growth, exponential decay, we're going to handle the same way. And solving this, let's see what we get. I'm going to do 0.98 to the 1/12th power. Get that, and subtract 1 from it. That's going to be 0.00168 something something something. Round to the nearest 100th of a percent. So that's equal to, moving the decimal over 2 spaces to the right, 0.168214. Again, you need a lot of places because once it's a percentage, 16.82%. Wait. I already moved it. I moved it twice. What am I doing? All right. And so rounding this, that will be to the nearest hundredth. That's going to be 0.17%. That is our monthly decay rate, rounded to the nearest hundredth of a percent. Cool. So lastly down here, I got some killer Regents problems. These are two Regents problems that tend to give people a lot of trouble. All right, and it has to do with the percent manipulations that we just talked about today. So a study of the annual population of red-winged blackbirds in South Carolina shows the population can be expressed by this function, where T represents the number of years since the study began. In terms of the monthly growth rate, the population of these blackbirds can be best approximated by which function? So it's telling us T represents the number of years since the study began. So in this original equation, they're giving us the yearly growth rate and the yearly growth factor, right? So 1.16, that is our yearly growth factor. We're multiplying by that each year. So what do we multiply by each month? So again, I'm going to take the 12th root of this, or I can raise it to the 1/12 power, same thing. And that's going to be about 1.012. That's going to be my monthly growth factor. Right, exactly like that oil problem we just did, where we took the 12th root. Same thing here. And so if I wanted to write a function, I can't use t anymore because t represented the number of years since the study began. Well, actually, I could still use t, but I changed it to a monthly growth factor, so I'm going to change this to m. So we started with 750 blackbirds. The monthly growth factor is 1.012, and that would be to the m power, because each month it grows by a factor of 1.012. So this would be a perfectly fine equation where m represents months, right? So this is not one of the choices, because the choices still use t in years. So how can I get this as a function of years? Well, how many months are in 12 years? Well, there's 12 months. Sorry, did I say how many months are in 12 years? I don't know what I said, but how many months are in a year? There are 12 months in a year, right? 12 months in a year. So if I want to change this to, in terms of t, I'm still using the monthly growth factor here, right? So 1.012. So after 1 year, if I plug in a 1 here, for example, well, how many times did I actually multiply by 1.02? I multiplied by 1.02 12 times in 1 year, right? So this should actually be 12m. So not 12m, 12t. All right, take a second and think about that. I know it's pretty confusing. All right, I'll do another example. If I want the monthly, or the number of blackbirds after 2 years, let's use this equation first. If I want the number of blackbirds after 2 years, wouldn't I plug in a 24? Right, because I know there are 24 months in 2 years. Right, and that'll give me the answer. So using this formula in terms of t after 2 years, right, t is number of years, b of 2 should equal, that's why it's 12 times 2. All right, so my answer is gonna be this equation. So that's the monthly growth factor here. right? But we're still using in terms of years, so that's why the exponent here changes to 12t. All right, and that is choice number 2. All right, so I'm actually going to put this question down here on the homework. All right, it's very similar. Try your best. It is somewhat challenging. This one's actually not as bad. All right, but that's going to be it for mindful percent manipulations. You have to be really mindful. You have to really think about what's going on. I would suggest plugging in some numbers after to see if your answer makes sense, like I did with the 2. And that's going to be it. Any questions, again, email me. Guys, talk to each other, post comments, and I'll see you guys next time.